Hello, this is section 6.2 for Calc AB, and today we'll be talking about volume using the disk and washer methods. So I know this looks a little intimidating, but it's actually really fun, and I think you'll really enjoy these problems once you get the hang of them. So the idea is we're going to take a curve graphed in the plane region, which is what we're used to, and we're going to revolve it around an axis of revolution to create a three-dimensional shape. Right, so that's what's kind of being demonstrated here. We're taking that curve, and you can see the curve there, and we're revolving it around, in this case, the x-axis. So the whole idea is as you're revolving around the x-axis, you can see that at the very end of section 6.1, we referred back to these rectangles, just refreshing your memory on, don't forget that to get the area under the curve, we're technically adding infinitely many rectangles. So we're going to take those rectangles, that whole idea, and as you're revolving, you end up creating a cylinder or a disk. We're going to call them disks. So you create a disk, and that's what's being demonstrated here. That's the disk created by that rectangle right there. And then we're going to take that same idea of adding infinitely many rectangles together, and now we're going to be stacking or adding infinitely many cylinders or disks together to give us the volume of this three-dimensional shape, right? So that's kind of what's being demonstrated here, is we're basically adding a bunch of cylinders together, or disks, okay? Now, the volume of a disk or cylinder is pi r squared. Remember, it's the base pi r squared times the height. Now, in this case, our disks are on their side, so that's why the W, your height, is technically the change in x. And then the pi r squared, the r, is actually being created by your curve. So the curve is giving you the radius of that particular cylinder as you rotate around. But that's where that formula is coming from. Okay? Now, the disk method is when you have a volume, it's a solid, so there's no holes in the middle. We're going to talk about that here in a minute. So we have a nice solid of revolution, and we're going to use the disk method. So you're going to first determine the radius. So that's the function. That's going to be determined by r. And the change in x, that's the width, or the height technically, because your cylinder is on its side. That's the dx right here. That's that part of the formula. So this pi r squared times the height, and then we're adding infinitely many of these cylinders together, disks, between A and B. So we're basically stacking them to give us the volume. So it's kind of cool. Now, if you're revolving around a vertical line, you're going to be in terms of y. So notice your bounds are the y values, your lower bound, upper bound, but it's the same formula, pi r squared times the height. And we're just adding infinitely many of those cylinders or disks together to give us the volume. And the radius is being determined by your function. That's that length here. Okay. All right, so the representative rectangle is always perpendicular to the axis of revolution. Okay. So set up and evaluate the integral that gives the volume of the solid form by revolving the region. So here's our region, and we went ahead and graphed the curve for you, sketched the region for you and that's just saying make sure you stop at the x and y axis. About the x-axis. All right, so if you are revolving around the x-axis, you're going to have to, you're doing the antiderivative with respect to x. So this needs to be a dx here. If you're revolving around the y-axis or a vertical line, it's going to be dy. Okay, and you can tell it'll change the shape of the three-dimensional figure depending on what you're revolving around. So it's really important you get that right. Okay, so the radius, so pi is just a part of the formula. Pi times, then we're going from 0 to 2. That's the bounds on the x-axis here. And then r, that's determined from the x-axis to your curve. That's the giving you your radius. So that's the 4 minus x squared, and then make sure you square it, because remember, pi r squared times the height, that's the area of one disk. And then, of course, your dx. And then you solve. All right? Let's try another one. So find the volume of the solid formed by revolving the region bounded by the graph. Okay, so I graphed that over here for us. And the x-axis, about the x-axis. All right, so again, same type of problem. Now this time they didn't tell us the bounds, so we'll have to figure those out. So you'll need to figure out where your function hits the x-axis. That's what I've done up here. Well, I actually completed the square to help us graph it real fast. Okay, so set your function here equal to 0. I'll explain the minus 0 here in just a second. All right, but yeah, set your function equal to 0 to figure out where it hits your x-axis, and then that gives you your bounds. So pi times the integral from 1 to 3, and then that's your radius, all squared dx. Okay. All right, set up and evaluate the integral that gives the volume of the solid formed by revolving the region, this about the y-axis. All right, so immediately, here's the graph. Now we're going about the y-axis. So you've got to get your function in terms of y. So I squared both sides, then did the square root. Now we're dealing with the positive part. That's the positive. So that's what we're going to keep. So then we did pi times the integral from 0 to 4, and that's going to be our radius there, squared dy. Okay, are you starting to kind of get the idea, hopefully? All right, now I've noticed over here, notice I'm writing the radius off to the side. That will become a little more useful coming up. So that's not a bad habit to get into, is writing the radius. And I'll explain here in a second why that's useful. All right, then here's another one. Set up and evaluate the integral gives the volume of the solid formed by revolving this function about the y-axis. So again, it's been graphed. It's already in terms of y, so this one's actually pretty easy. You can see the radius goes to the y-axis. So pi times the integral from 1 to 4 of your radius squared dy. Pretty straightforward. Okay, now here's where things get a little interesting. All right, so set up and evaluate the integral that gives the volume of the solid formed by revolving the region y equals 4 minus x squared over 4 about y equals 2. Okay, so first we're going to want to figure out where that curve intersects that horizontal line. So that's what I've done here. I set the curve equal to 2 and got my intersection points there. All right, so now up here I wrote notice I wrote the radius of our curve and I put minus 0. Technically, you've always been doing that to get the radius. You're stopping at that x-axis right there. And that becomes important with this example because you're not going all the way to the x-axis. You're stopping at 2. So that's going to affect your radius. So now we're going to want to do 4 minus x squared over 4, but minus 2. Because we don't want to include all of that. We want to cut off the rectangle at 2. So that's why the radius is changed to 2 minus x squared over 4. So when I go to set it up, pi times the integral of those two intersection points there, my radius is not 4 minus x squared over 4, it's now 2 minus x squared over 4 to cut off that part that I don't want. All right, dx squared dx. And then you solve it from there. So just a little bit different. Okay, so the washer method is, it's basically the disk method can be extended to cover solids of revolution with holes by replacing the representative disk with a representative washer. The washer is formed by revolving a rectangle about an x-axis. If R and big R are inner and outer radii of the washer and W is the width of the washer the volume is given by. So basically, you're going to find the volume of the outside. That's your big R. You're going to find that volume, and then you're going to subtract the part that you don't want. So that's what's happening there. Okay. So, and this is the formula right here. So you're going to want to find the volume of basically the outside disk, the big disk, using the big R. And notice all of these up here, I always labeled them as big R, always capital R, because we didn't have a hole to subtract away. So now we've got this inner disk that we want to get rid of, so that's what we're going to call little r. So it's always big R minus little r. Okay. So look for a gap between the axis of revolution and the region being rotated. So now I'm going to redo this problem we did here, example 5. So set up and evaluate the integral gives the volume of the solid formed by y equals 2 and y equals 4 minus x squared over 4, revolving the region about the x-axis. So this is an entirely different three-dimensional shape. Now it's kind of almost like a bead, almost, you know, like a little bead you put on a necklace. Okay, so now you are dealing with a big R and a little r because there is a part that you want to subtract away. If there's a hole, you have to think now in terms of big R and little r. So my rule of thumb is locate your axis of revolution, which is the x-axis. And I've looked for the function that's farthest away. That's going to become your big capital R. So that's what I wrote over here. That's capital R. And then the function that's closest, the part that you want to subtract away, is what we're going to call little r. And once you've established that, it's not too bad. So pi times the integral, we already found those intersection points from the previous example, and this will be your big R squared minus your little r squared dx. And that's it. And you'll notice you get a different answer because it's a different three-dimensional shape. Here it was just a solid, kind of like a football or a Nerf gun. But in this case, it's a different, you've got a big hole in the middle. Okay, so let's try another one. Find the volume of the solid generated by revolving the region. So we've got two different graphs here. We're going to first revolve around the x-axis. So that's here. That's what's in blue. All right, so we need to determine, we definitely can see that there's going to be a big hole in the middle. So as you take this region and revolve it around the x-axis, there's definitely going to be a hole. So we need to establish first the big R, and that goes all the way to the x-axis. That's your most outside function. And then your little r is the line here. So then we're ready to set it up. Pi times the integral from, find the intersection points, looks like -3 to 0, big R squared minus little r squared. And that's it. Now, be careful. A really common mistake is subtracting and then squaring it. You need to make sure you square them separately. Okay, now same problem, but now we're going to revolve around y equals 3. So that's this red line here, y equals 3. So your big R is going to be the function that's farthest away minus where you stop, which is 3. What we did up here, it's still the same thing, big R minus, but you stop at the x-axis, which is 0. Okay, but in this case, since we're stopping at 3, it'll be big R minus 3. So that's what's happening. And then little r, same thing, little r minus 3, which is x minus 6, or x plus 6 minus 3. So then you do the same idea. I got lazy and just wrote r squared minus little r squared. Okay. All right, so here are just some more examples. So graphing, revolving around the x-axis. So this one, the hole's not as obvious, but there is definitely, it's not a hole per se, but there is a part that you need to subtract away. It's not a solid. So we established our big R and our little r and went from there. Find the volume of the solid formed by revolving the region. So here's our region about the y-axis. Okay, so this one's interesting because it's you're revolving this region here about the y-axis. So immediately when you go to establish your big R and your little r, you might recognize as you go from right to left, this function's always the farthest away, but the little r changes. This top part is actually a washer and the bottom part is a disk. So you'll have to break this up into two separate problems. So this part here is what I'm doing here. That's the disk. Pi times the integral from, make sure you use the y value, 0 to 1 of 1 squared dy. So that's that vertical line there. That's the disk plus, and then now we switch to washer method. So going from your axis of revolution, the farthest away is that vertical line. So that's your big R squared. So that's your 1 squared minus, and then this function closer, which is y, the square root of y minus 1 squared dy. So a little bit different, but you do have to be careful and make sure you break it up, just like when we did the area of the region between the two curves. Okay, just make sure you read through these errors, be sure you do your homework, and let me know if you have questions.